All right, so section 12.2, we're going to be working with calculus on the vector valued functions that we were sort of defining last time. And a lot of what it's going to feel like is it's going to feel like we're going to be doing chapters 1, 2, 3, 4 that you did back in Calc 1, but now we're going to be doing it with vectors. Okay, so a lot of the components are going to be the same. It's just going to be done sort of in triplicate because we're going to be doing things in three dimensions. Okay. All right, so to start with, we're going to take a definition. 2.1. Do you remember where you started in calculus? What's the very first calculus component that you learn about? Very first. Limits. Excellent. For a vector valued function, R of t, defined just like we did last time, which was FGH of t. The limit of R of t as t approaches A is given by taking the limit of each of the components. So we're taking the limit of f of t as t approaches A, the limit of g of t as t approaches A, and then the limit of h of t as t approaches A. Provided the limit exists. So we're going to say provided all indicated limits exist. And then we'll sort of put a note down here. If any limit fails to exist, then the limit as t approaches A of R of t does not exist. Okay, so one of the first things you should probably do when you're working with any of these particular problems is to look and see if any of them is going to fail to exist, right? There's no sense in finding two limits to just find that the third one fails to exist and you didn't need to find the first two. Are you with me? Okay, so some of the problems you have, they'll work on two of the components and not work on one of them. So, all right, so we're going to do example and example. The directions saying find the limit if it exists. This is the limit as t approaches 0 of sine of t over t, cosine of t, and t plus 1 over t minus 1. Okay, so take a moment to pause before you start plugging anything in anywhere and process through all three components to make sure that you really want to process through the three components. So what kinds of things are you thinking as you're looking? The first one looks like it might fail, but yeah, and I chose this one on purpose because I wanted to make sure you remembered that fact. This is a special limit that you learned somewhere along the way. Whoops. That the limit, as t approaches 0 of sine of t over t is actually equal to the value. What was it, Caleb? 1. But yeah, I mean, looking at it initially, you might have first thought, hey, wait a minute, that's going to mean a 0 in the denominator, and you had to pause to remember, is there something else going on here? And there actually is on this one. How about the cosine of t? That one okay? We can evaluate that one. How about t plus 1 over t minus 1? Yeah, that one's also good. All right, so this limit does exist. We already found the first component. It's 1. What's the second component? It's also 1. And then the third one? It's -1. Okay. So what kinds of things might you have to do besides recognize that sine of t over t is 1 as the limit goes to 0? Well, you might have to do some factoring, right? You've had to do that before where you've eliminated maybe a denominator or something going on. You might have to consider something like a square root and whether or not a value is underneath a square root actually valid, those kinds of things. You might also have to consider, I think there's one in there, I can't remember if it was one I assigned or not, where you had a tangent value or a secant value, and some of those have asymptotes, and you have to make sure that you're not actually ending up on one of those asymptotes or something like that. Okay, any questions on that one? Okay. Do you remember what you did after you did limits? It's right after, before derivatives. Yeah, do you remember what the epsilon and deltas were for? You're exactly right. I mean, epsilon and deltas were related to limits, right? They have limits components in there.
Delta H?
They had to do with continuity, right? Limits and continuity are very related topics, but it has to do with continuity. So that's the next piece that we're going to look at here. So definition 2.2. The vector valued function R of t, again defined just like we've been defining it up till now, is continuous at t equal to a whenever the limit as t approaches a of r of t is equal to r of a. This is the same definition about continuity that you had way back when. It's just that it's being defined now for a vector valued function instead of for a traditional function that we've looked at until now. So, like for instance, on the last problem, this wouldn't work. That last example that we did, we found the limit. We found the limit as t approached to 0. But it has a problem. The problem is that you can't actually plug in 0 into the first function, right? Like it is actually not on that point. It's not a value in there. That's a problem. So this first vector valued function r of t would not be continuous at t equal to 0. That would have a problem spot. It also wouldn't be continuous at t equal to 1, right? So we're looking for pieces where it fails to be continuous, typically, not where it actually is continuous. We look at the failure spots usually. So one more component of this before we do an example, theorem 2.1. A vector valued function r of t is continuous at t equal to a if and only if all of f, g, and h are continuous at t equal to a. And believe it or not, that's exactly what we were sort of describing as we looked back at the last function, right? This is just, all this theorem is it's a combination of this definition 2.2 with what it means to be a vector valued function with limits back in definition 2.1. So it's just a combination of these two definitions. All right, so we're going to do an example that's asking us to determine all values of t at which the vector valued function is continuous. And the function that we're going to be using, r of t, is cosine of 5t, tangent of t, natural log of t. We're just going to go through this component-wise, like the last theorem said that we could do, and take a look at things that would sort of cause us problems with continuity. So let's start with the cosine of 5t. What can you tell me about the cosine of 5t in regard to continuity? It's continuous everywhere, absolutely. There's no t value that I can put in. It's cosine, right? Cosine has that nice wave shape, no problems with continuity. So this one is continuous everywhere. So I'm going to say it's continuous for all, oops, t is my variable, for all t in the real numbers, okay? How about tangent of t? It is not continuous at a lot of places. Do you remember how you decide those places, or do you remember where those places are? Somebody tell me one place where it's not continuous. Yep, those asymptotes. Do you remember where any of those asymptotes are? Pi over 2. All right, so the first one is at pi over 2. Oops, let me write this down. So this is continuous for all t in R, as long as t is not equal to some things, right? The asymptotes. Pi over 2 is the first one. What's the next one? 3 pi over 2, and then 5 pi over 2, and also the negatives of all those, right, Nathan? Okay, so how can I write that in a condensed way? Do you remember from trig what you do? And I'm just going to put plus. We could do plus or minus. I'm going to write a little bit differently. Plus, what did you want to write, Nathan? N pi or k pi? Yeah, I'm going to use k. I think your book tends to use n. This particular book, the last book I've used, tended to use k. K here is an integer. Well, let's use some notation just because we can. So k is an integer. Does that look like notation y'all have seen before? K is an element of the integer, C is integers. And Nathan, that's the reason I'm going to use the plus there between them, is because since I'm using integers, I get the minus for free. Yeah. Okay, so I get continuity everywhere except the half pies, right? I mean the true half pies. All right, how about natural log? We encountered one of those last time, didn't we, Joel? Right. So this is continuous for all t greater than 0. Okay, we have to have a t value bigger than 0 to put inside of a natural log. So I need to take all of these sort of details that are separated and I need to combine them into one statement, because that's the question. The question is asking, where is this vector valued function, which has all three of these components, going to be continuous?
Should we just take away the minus from the plus or minus then?
Yep, we could. So this is continuous for all t and r, such that would be one way to do it. T is not equal to, well, we have to be careful, pi over 2 plus pi k. Is this what you wanted me to write down?
Yeah, because I mean,
We still need one more detail. It's positive. So we need to say that t is positive. Right? Positive t values that are not the half pies. Okay? Is everybody all right with that? Okay, so you guys didn't want to do continuity next. You wanted to do what? Limits and then derivatives. So that's what we're going to do next, derivatives. Definition 2.3. The derivative r prime of t of the vector valued function r of t is defined by, and you're not going to like this definition, write it down and then we'll work through the details in a minute. R prime of t equals the limit as delta t goes to 0 of r of t plus delta t minus r of t over delta t. For any values of t for which the limit exists when the limit exists for t equal to some value a, we say r is differentiable at t equal to a. And that looks uncannily like a limit definition you have seen for derivatives before, right? Yeah. The only difference you're noticing, of course, is that the delta t is where we previously had h. Yeah. Now, in practice, after you learned the limit definition of derivatives, which you all loved, you learned simple definitions or simple rules for finding derivatives, right? And we're going to be using those for in practice of what's going on here too. So this is theorem 2.2. Let r of t equal the function f of t, g of t, h of t. And suppose f, g, and h are differentiable. For some value of t. Then r is also differentiable. At that value of t. And r prime of t is what do you suppose? No surprises. What is it? F prime of t, g prime of t, h prime of t. So we're just doing sort of a three-component derivative, right? Yeah. All right, so here's the example we're going to do. Oops. Find the derivative. First component is e to the t squared. The second one is t squared e to the 2t. And the third one is the secant of 2t. And yes, I chose something purposely fun to help you remember some of your derivative rules. First component, e to the t squared. What rule are you going to have to be using on that? That's a chain rule. All right, so what's the derivative of e to the t squared going to be? What was that?
So
Yes.
E to the t squared times 2t.
Okay, so 2t e to the t squared. Everybody good with that one? What rule are you going to be using on the second one? Product and chain. The chain rule is not a very exciting chain rule, right? But yeah. All right, so product rule. Somebody tell me what I'm going to have.
2t e to the 2t plus t squared 2 e to the 2t.
Okay? Is everybody good with that component? Look okay? And possibly the hardest one of all of them, simply because we don't use them all the time, is secant. Secant tangent. And a chain rule. So the chain rule is just going to give me that exciting 2, right? And then I'm going to have secant of 2t, tangent of 2t. So good? No problem? All right. There's one different thing that we're going to write down here next. It's going to sound like we're going to draw something. We're not going to draw anything. But if you have your calculators, I want you to be able to see from your calculator how to take a picture of what's going on here. So grab your calculator out, and then I'm going to define one more. Oops. One more, this isn't our last thing, I don't want you to make it sound like that, but one more definition doesn't even have a number, that's how exciting it is. So we say a curve traced out by a vector valued function R of t equals f of t, g of t, h of t is smooth on an interval I if R prime is continuous on I and R prime of t is not 0 except possibly at any end point of I. All right, so we use this word smooth when we talk about derivatives. This is a little different, though, when we did it in 2 dimensions with functions. When in the world was it, or what kind of an image would you have had when you would have had a graph that wasn't smooth? Can you give me some sort of problem spots when we did this in Calc 1?
There's the absolute value, like
Yeah, where it sort of met at a sharp point, right? And sometimes it's called a cusp. An absolute value function is a really good example of a graph that is continuous. I mean, it's definitely continuous. You don't have to pick up your pencil or anything. We can use epsilon delta arguments. It's continuous. but it's not smooth, right? There's that location where it has this sort of a directional change. And so the way we found that directional change is the derivative didn't exist. So here the derivative is going to exist, right? That's what it says. In fact, the derivative is going to be continuous as well, not just the graph, but the derivative is going to be continuous. But if the derivative has a location where it's equal to 0, then we're going to have this problem with smoothness in our graph. So we're going to do an example. We'll do it out, and I'll have you take a look at your calculator to see that it matches what we're saying it actually should look like. All right, so here's our example. We're going to determine where the given curve traced out by R of t is smooth. And our R of t is t to the fourth minus 2t squared, and then t squared minus 2t. So, using the definition that we just had from the previous slide, what are we going to have to check for?
R prime of t equals 0.
Yeah, and we also need to make sure that R prime of t is continuous. So we're doing things in regard to R prime of t. So let's find out what R prime of t is. All right. So what is R prime of t? This one's a nice clean one for you compared to my last one. What do you have? 4t cubed minus 4t, 2t minus 2. All right, so first issue, R prime of t is continuous. Why? Yeah, and it's continuous for all t, right? So for all values of t that this works. So for all t, this is continuous. And the reason is because the components are polynomials, is why. And polynomials are continuous everywhere. So that's the reason for it to be continuous. The other thing that we were testing, though, the more sort of crux of the issue has to do with where these things are actually equal to 0, right? So we need to figure out where that happens. So what are we going to do next? What's that?
Set them equal to 0.
Yeah. We need to see if we have sort of issues with them both being equal to 0, a location of any of those. So oops, sorry. That one should say equals 0 as well. Second one's easier to do. What's the second one going to give me? T equal 1. What about the first one? Possibly t equal to 0, and there's also here a, do you know? 1 and negative 1, actually. But, and again, this is unfortunate that I'm writing instead of having it typed, but this is a vector function, right? Right, this is a vector, and this is the vector 0. So the vector 0, 0 means that we've got to find a t value for both of them to be 0 at the same time, or it's not the vector 0, right? The vector 0 would actually be the vector like this. Okay, at any other t values, like if I use t equal to 1, the second component, I'm sorry, not t equal to 1, t equal to 0, right here, if I use t equal to 0, I get 0 in this first component, the x component, but the second component doesn't give me 0, which means I don't have the 0 vector. Are you guys with me on that? It's only got to be the 0 vector. I mean, it has to be the 0 vector. Both components have to be 0. So I'd like for you to take a look at your graph. Try to think. I'm trying to think how you graph it. I know I was thinking through it yesterday on how to do it. I think you can do it in parametric. So take your graph, put it in parametric mode, and then in parametric mode you should be able to put in this component for x and this component for y to get a graph of this function that should have a cusp, right, a point where it's not smooth at t equal to 1.
Not quite like that.
Let me take a look.
What value is the cusp at -1?
Well, so when you take a look at this graph, if I plug in t equal to 0 here, I get -1, -1. So on your graph, you have something that looks like this going on, and this location right here that you're seeing happen is at the x value -1, y value -1. That's where the sharp turn or change in direction is happening. And it wouldn't even have to be that sharp. And this one was very sharp, obviously. But anything where it changed in direction, it wasn't a smooth, the derivative from both sides, in other words, don't match. We would have that location. Okay. Along with this idea, we're going to do another, and this one's a little bit off the beaten track of what we've been doing with other components of calculus, but it does come back into play with what we did in Chapter 11. So we're going to find all values of t such that r of t and r prime of t, so the vector valued function and its derivative, are perpendicular. Okay, so we'll do this kind of one piece at a time. The function we're going to be working with on this one is t squared t squared minus 5. Okay, so even if you don't know how to deal with the perpendicular part at the moment, which you might not remember, but we definitely have to find r prime of t, right? I mean, that's a for sure given piece of information we're asked to find here, so let's start there. What is r prime of t going to be? Two t, 1, 2t. So far, so good? All right. Now think with me back into Chapter 11. How did we decide if two vectors are perpendicular? You did it on your test.
Is it the cross product equals 0, or is it the dot?
The dot product.
Yeah.
Yeah. If the dot product is equal to 0, then the two vectors are perpendicular. So we're going to find the dot product. So let me make that note in here. You can remind yourself. So from Chapter 11, r and r prime are perpendicular if and only if r dot r prime is equal to 0. So we're going to do the dot product of these guys. All right, so the first piece in the dot product, I've got t squared times 2t, which gives me 2t to the third. Second component, I've got t times 1. Third component, I've got t squared minus 5 times 2t. Minus 10t, right, good. So this is my dot product, and I'm supposed to be able to try, or I'm supposed to be trying to figure out where is this, or is this ever equal to 0, right? And if so, at what t value that would happen. So we'll simplify what we have here. I've got 4t cubed, and then minus 9t. Is that right? Okay, now what? What was that? I can pull out a t. Very good. Oh, I'm sorry. Yes, you're right. Yep, 4t squared minus 9 equals 0. All All right, what values of t am I going to get on this? T equals 0. What else?
Positive, negative, 3/2.
Positive and negative 3/2. So there are 3 locations where the derivative and the actual function have are going to be perpendicular to one another. All right, there is one thing left in this section that I haven't done. Any idea about what in the world it might possibly be? It's integrals, that's right, antiderivative. All right, so the one component that we haven't done left in this section is integrals. I would like to go ahead and write the homework down for you. You don't have to have it finished before you come next time, but you'll know exactly where the integral section is that we haven't done. But the sections that we have done, you can go ahead and get them taken care of so that you don't end up with 2 sections of homework or whatever between Wednesday and Friday. So this is 2, 5, 9, 12, 15, 18, 22, 25, 32, 35, 38, 39, 42, and 43. That's it. I stopped. I think 5 of those are antiderivatives. So the other components are going to be derivatives, limits, the smooth and continuity, those kinds of things for next time.